In 2022, the US government announced its goal of wanting to reduce the level of carbon emissions to a net zero by the year 2050. But considering that the United States alone produces more than 14 trillion pounds of CO2 equivalents a year, we still have a long way to go. An alternative source of energy that's garnered much interest over the past couple decades is hydrogen gas. Fuels that are powered by hydrogen emit less greenhouse gases as opposed to its counterparts like petroleum or natural gas. However, we can't necessarily replace the conventional fuels to hydrogen because the reactions that are used to produce hydrogen are currently carried out in rather extreme conditions and are costly. Converting molecules like water or methanol into hydrogen requires a metal catalyst such as platinum to initiate and speed up the reactions. And here's the problem. Platinum is a rare earth metal, so platinum is expensive. To address this issue, we can try to reduce the amount of platinum that's required as much as possible to the point where a single atom of platinum can effectively catalyze the reaction, leading to the design of what's now called single atom catalyst. For platinum, these atoms need to sit on a support material that will remain stable throughout the whole reaction. We were particularly interested in transition metal carbides as a low-cost support material for stabilizing platinum due to its many favorable properties, such as having a high melting point, high conductivity, and chemical stability. Our computational collaborators then surveyed all the different metal carbides to simulate which material would be a good support to stabilize platinum based on parameters such as binding energy and activation energy. We then synthesized the platinum single atom catalyst using 4 of the top candidates, that is tungsten carbide, vanadium carbide, tantalum carbide, and hafnium carbide, then imaged our samples using a special microscope called an STEM to get atomic resolution. From these images, we found that hafnium carbide formed a promising conformation where it formed single atoms of platinum as opposed to clusters of platinum. Currently, we're working on additional tests to evaluate the activities of our catalysts. So by identifying thermodynamically stable and favorable support materials to stabilize platinum, we can design better catalysts that will produce hydrogen in milder conditions and at a lower cost, effectively pushing towards the goal of reducing carbon emissions. Thank you.